we've seen how we can condense and represent the whole data set using just one measure of central tendency, such as mean or median. But there is a problem with representing the whole data set using just one measure that we are going to take a look at in this video. So consider these two data sets, one in which we have 14, 14, 14, 14, 18, 18, 18, 18, and another data set in which we have all 16s. If you calculate their mean and their median, they both come out to 16, both for this guy and for this guy. Now the problem is, if you were representing the data only using either mean or the median, you would see that these two data sets are the same. Whereas you can see just by looking at the data that they are quite different from each other. This guy has a lot of spread, so it has a lot of spread, whereas these guys are the same, right? So we need another measure alongside a measure of central tendency which can measure the spread. So let's consider this in a little more detail because it's extremely important. These are the two data sets. So one data set here and another data set over here. Now, just by looking at them, which one would you say has more spread? Number one or number two? So I'm fairly sure that you will agree that number two has more spread. What we want to do in this video is somehow quantify this intuition that the things which are wide on a number line have a larger spread, and those which are closer together have a lower spread or a lower dispersion. So this is called the concept of dispersion. How far away is your data from your mean? So this red line over here is the mean, and we want to somehow quantify how far away things are from this mean. So just taking this intuition to a quantification, we are going to define dispersion as the average distance of values from the mean, right? So that makes sense. So the higher the distance, the higher the dispersion or the spread. So how do we calculate the average distance? Just as we calculate the average for anything, we are going to first calculate the mean. So that's fairly easy. We take all the values, sum them together and divide by n. So we get the mean, which we are going to represent as x bar, right? So x are all of our values. We are going to calculate the mean first. Then we are going to take a look at each data point individually. So this guy, and we are going to calculate the distance it has from the mean. We are also going to do the same for all the other data points, right? So we are going to add up all the distances and then we are going to divide by the number of data points. So for instance, let's take this guy. So let's say this is at 16. So we are going to say 16 minus 14 is equal to 2. Let's take this guy over here. So let's say this is 13. Now, if we were doing this 16 minus 14, then we have to do 13 minus 14. And that means this is going to be minus 1. But we're not really interested in the direction in which the distance occurs, either positive or negative. We are only interested in the magnitude of the distance. How far away is it, whether to the right or the left? So what we want to do is we want to convert this minus 1 into a plus 1. And it's fairly easy. So if you are taking any value minus another value and the values can come out as negative, all you have to do is simply go ahead and take the absolute value. So that gets rid of the negative. But there is a problem with this absolute value. And this is a little bit of calculus. You don't have to understand calculus in order to understand this concept. I'm going to give you a brief intuition about this. And if you don't recall calculus, that's perfectly fine. I'm just going to do this for the sake of completeness. So let's say you have this graph. You will recall that absolute function, the absolute value function looks like that, right? So for any positive value, it's positive, and for any negative value, it's also positive. That's fine. The problem with this is that it is not differentiable, which means, which means it does not have a derivative defined at this point, at 0, or at its lowest value. And oftentimes in machine learning and data science, we are interested in this very point, the point in which the derivative is not defined. So we generally tend to not use the absolute function. We have another function which can do the same thing. It can get rid of the minus sign, and that function is the square. So if you take this, so this squared is going to be 4, this squared is going to be 1, and let's say this guy over here, so 16, so 28 minus 14 is equal to 14, and we're going to square that as well. Okay, So here's what we're going to do. We are going to take each point, we are going to subtract the mean, whatever comes out, we are going to square it. Okay. We sum all of them together and then we divide by the total number of data points. This is now our average distance of values from the mean, except we've done something else. We have squared all of them. So we have average squared distance of values from the mean. Because we're interested in a numerical representation, we now have dispersion defined in a singular quantity. And here's the formula for that. So let's write this concisely. So we are going to take all the data points, we are going to subtract the mean from that data point, square the value, sum them all together, and then divide them by n. This gives us the value of this guy over here, which is called the variance. It's written sigma squared. So sigma squared, right? So you read that as sigma. So sigma squared is the variance, and variance is the measure of dispersion that we use. This is very commonly used, and it's generally misunderstood. People don't really understand the intuition behind variance. If you start from this method of defining variance as the average distance of values from the mean, and just because the distance could be negative and we don't want to use the absolute function, we squared it. So now this is the average square distance of values from the mean. All it's saying is how far away are things from our mean, okay, on average. So the problem with this is, if our original data units were, let's say, in meters, our now variance units are in meters squared, because we squared everything over here. So that is generally a problem for humans, because if you change the units, it's very difficult for us to understand and reason with it. For instance, how do you compare miles with kilometers? They're the same unit sort of, but slight differences make it difficult for us to analyze which is larger, like 600 kilometers or 600 miles, right? It's difficult. So the solution to that is we take the square root of variance. So variance was sigma squared. We take the square root and we get the value of sigma, and this is called the standard deviation, right? So standard deviation is another very important concept. So what standard deviation is we took the variance, so average square distances of values from the mean, and we took the square root. So standard deviation is the square root of average square distances of values from the mean. If you read it like that, it sounds complicated, but if you follow from the beginning of this lecture, you will realize that it's just how far away are the values from the mean. That's all there is to it. How far away are values from the mean? That is called standard deviation. We are going to visually represent these in the next video. Here, I just want to include another measure of dispersion. So we've seen variance. We've seen it's written as var often. We've seen standard deviation, which is typically written as SD. And there is another measure that we want to see. For that, we have to see what the problem with standard deviation is. So let's take two values. Is the value of 10.7 a large standard deviation, or is the value of 1094 a larger standard deviation? If you look at the numbers, it seems that 1094 is a larger standard deviation. That makes sense. But it really depends on what the mean is. For instance, if for this guy, our mean, the data in which this is the standard deviation, our mean was at 100. And the data for which this is the standard deviation, our mean was, what was that? 100,000. Right? So these were our means. So here the standard deviation divided by the mean into 100 is 10.7. So standard deviation is like 10.7%. And here the standard deviation divided by the mean into 100 is 1.09. So these are in percentage. So now you can see that the first standard deviation is quite large because it all depends on the mean. So this is the last measure of dispersion. This is called the coefficient of variation, which is just taking the standard deviation, dividing that by mean and multiplying by 100. So this is a relative measure of dispersion. It's essentially dispersion or standard deviation represented as a percentage of the mean, right? So it's not very often used in computer science. Statistics people typically use that, but for us, standard deviation and variance especially is a lot more important. In the next video, we are going to take a look at a visual representation of both of these.